NASA just caught 3I Atlas changing again, and this one is serious. Its rotation is speeding up, its spin period is collapsing, and a second active region has appeared in the light curve. Inside the coma, a twisting spiral structure has now emerged, a sign that powerful jets are putting real mechanical stress on the nucleus. If this acceleration continues, the object won't hold together. It could literally tear itself apart from centrifugal force. Stick with me, hit subscribe, and drop a like. You're going to want to see where this is heading. It became clear that the object we have been watching is still changing in ways that do not fit what we usually expect from a comet-like body. The update came quietly, as most scientific updates do, but the shift inside the new data was strong enough that the teams following this object paused for a closer look. For weeks, observers had tried to treat its behavior as something within the familiar range of activity we see in ice-rich bodies moving near a star. Yet with each new measurement, the pattern repeated itself. Just when the data seemed to settle, the next observation introduced a different detail. Over time, this steady chain of surprises has made it harder for researchers to rely on standard explanations. Today's measurements added one more link to that chain, and it was not a small one. 3I Atlas is more than a visitor passing through. Because it comes from beyond our solar system, almost every part of its behavior teaches us something about environments far from the Sunday. That is why teams track each variation carefully. Even small changes matter when the object itself formed under conditions we do not fully understand. A typical comet in our solar system shows a style of behavior that is familiar. Jets of gas rise as sunlight warms the surface. Dust lifts into a cloud around the nucleus, and the rotation of the core remains fairly steady unless something dramatic happens. This object has followed some of those steps, but it has also stepped outside those patterns, often enough that each new update brings renewed attention. The activity in recent days focused mainly on the material leaving the surface. When jets release gas and dust, they can shift from hour to hour, especially when sunlight falls unevenly across the nucleus. Observers looked closely at how much material left the object, how wide the cloud around it became, and how the shape of that cloud changed as it drifted through space. These are common questions when studying comet-like bodies, and the answers help researchers understand the rate of heating, the structure of the outer layers, and the stress placed on the surface as it warms. Most of the conversation centered on these effects, because the changes were visible in the bright halo surrounding the object, a region known as the coma. This halo offered hints about surface conditions and helped predict how the object might evolve as it continued its path. But today's update had nothing to do with the material leaving the object. Instead, it focused on motion on the way the nucleus inside the coma is turning. Rotation may seem simple at first, yet it plays a major role in how a small body moves through space and how it responds to heating. To understand rotation, teams do not need to see the nucleus directly. They look at the brightness of the object over time. A nucleus is rarely round. It has uneven surfaces that reflect different amounts of light. As the object rotates, brighter and darker sections turn into and out of view, creating a repeating brightness pattern that reveals the length of one full rotation. When the pattern stays steady, researchers know the spin state is stable. For several days, that stability held. The brightness curve repeated with a regular rhythm, completing a cycle every few hours. Small fluctuations appeared here and there, but nothing large enough to draw serious attention. A stable curve meant the object's rotation was under control, with no major forces acting on it strong enough to change the timing. That steadiness provided something rare in this mission, a baseline with so many things shifting around the object. This one measurement seemed predictable. That sense of predictability changed with the latest data. When tracking centers compared the newest brightness measurements with the earlier pattern, the alignment no longer fit. Peaks of reflected light that had appeared at the same point in each rotation yesterday were now arriving earlier. The shift was not large in magnitude, but it appeared every time the new data were placed against the older curve. A single mismatch might be noise from the instruments or a temporary effect caused by dust crossing the line of sight. But when the difference repeats itself again and again, it points toward an actual physical change. To understand why this matters, it helps to look at how rotation usually changes in small icy bodies. Jets of gas moving outward from the surface can create a gentle push, much like the small thrust from a slowly leaking valve. When an object vents material unevenly, these pushes can build up and slightly alter the rotation speed. Over long distances, even a small amount of thrust can shift a rotation period by minutes or hours. Researchers have seen this effect in many comets within our solar system, but it usually happens when the jets are strong and well defined. In 3I Atlas, the jets have been present but not stable, and none of them appeared strong enough to explain such a clear change in the timing of the rotation curve. That is one reason today's update drew so much attention. A shift in rotation can also come from internal changes. As a nucleus warms, ice beneath the surface can expand or escape through new cracks. This release of energy can redistribute weight inside the body, and when the mass shifts, the rotation can shift as well. But this kind of change is often irregular. It does not usually produce a neat, repeating adjustment like the one seen today. Instead, it shows up as noise in the brightness curve, creating bumps that fade or appear at random. The new pattern did not look random. It looked orderly. It looked like something in the object's motion had taken on a new pace. Because researchers cannot see the nucleus directly, they must rely on these indirect signs. Brightness curves are one of the most reliable tools available when studying distant small bodies. The method has been used for decades to track asteroids, comets, and even distant moons. When the peaks and troughs shift in a consistent direction, it is usually because the body is rotating faster or slower than before. Today's data shows the peaks arriving earlier, which strongly suggests the rotation is speeding up. The amount of speed change is still small, but any measurable shift over such a short time is worth examining. A change in rotation can influence other behaviors as well. When a small body spins faster, the way sunlight hits the surface changes. Areas that once warmed slowly may now warm more quickly. That change can alter the release of gas and dust, which then adds new forces that act back on the spin state. It becomes a cycle. Rotation affects venting, and venting affects rotation. In comets from our own solar system, this cycle usually moves toward a gentle balance. But 3I Atlas has not followed the usual path, and that makes each new development important for understanding its overall evolution. With today's measurements, the sense of a steady baseline, one of the few stable elements in this mission, no longer holds. The rotation period is moving, even if only slightly, and the shift has appeared often enough that researchers cannot ignore it. Each time the brightness curve is compared with the earlier data, the mismatch repeats in the same direction. The peaks continue to arrive ahead of schedule. The shift is small but measurable, and most importantly, it is showing up consistently. The first clear sign that something important is happening comes from the change in the rotation period. The object is no longer turning at the same pace it held just days ago. The new measurements show that each full rotation is now slightly shorter than before, which means the nucleus is spinning faster. The difference is small when you look at a single cycle, only a fraction of a second, but rotation is repetitive. When a body spins again and again through hundreds of cycles, even small differences grow into patterns that can be measured with confidence. Each cycle ends just a little earlier than expected, and when researchers place the new brightness curve over the old one, the shift appears in the same way every time. A change of this type means a real physical force is acting on the nucleus and increasing its rate of rotation. A spin-up caused by jets is not unusual for comet-like bodies. When sunlight warms parts of the surface, pockets of ice can turn into gas and escape through vents. These vents act like tiny engines, sending material outward. Because of the conservation of angular momentum, when material flows out from an off-center location, the nucleus experiences a push in the opposite direction. Over many cycles, this push can gradually change the rotation speed. This basic principle has been used to explain changes in the day length of several icy bodies observed in the past. But while the mechanism is familiar, the current changes in 3I Atlas raise questions because of what else is happening at the same time. Jets alone do not explain the entire pattern, especially when the timing shifts and the shape of the brightness curve both evolve together in a coordinated way. The shape of the brightness curve tells researchers more than just how fast the object is spinning. It also shows how different surface regions contribute to the total reflected light. In earlier observations, each rotation produced one strong peak and one smaller rise in brightness. The strong peak likely came from a broad reflective area or from a region with steady activity. The smaller rise hinted at a weaker or less consistent area. Yesterday, that pattern matched our expectations, but in today's curve, the smaller rise is no longer small. It has grown until it is nearly equal to the main peak, which means a second region on the nucleus has become almost as active as the original dominant one. A change like this matters because it tells us that the forces acting on the nucleus are becoming more complex. When one jet is active, the rotation usually changes in a simple and predictable way. When two regions become active at the same time, and especially when they produce jets in different directions, their combined effect can twist the nucleus in a pattern that shifts over time. Each jet may carry a slightly different amount of material. Each one may warm or cool at a different rate. As the nucleus rotates, the angles of these jets relative to the sun change, which alters their intensity. This makes the mechanical forces on the nucleus uneven, and uneven forces tend to create uneven motion. This is why the rotation curve no longer looks the same as before. To picture this more clearly, think of the nucleus not as a smooth sphere, but as an irregular body with slopes, ridges, and patches of ice buried under dusty layers. As it turns, the sun heats different sections depending on their angle and location. A jet on one side might release gas in a steady stream, adding a push at the same point in every rotation. A jet on another side might activate only when a rough surface catches enough warmth. When two jets operate this way, their combined thrust acts at different times and different angles. Over hours, this can create a twisting motion that slowly shifts the rotation axis or changes the speed of rotation. The new brightness curve reflects these internal changes, showing that the distribution of active regions on the nucleus is no longer simple. Researchers cannot see the nucleus directly because the coma hides it beneath a cloud of dust and gas. Instead, they examine the inner coma, the region closest to the nucleus where the material is densest and where newly released gas and dust still follow the direction of the jets. Normally, this region appears as a smooth, diffuse glow because most of the details are lost in the bright surrounding light. But advanced image processing can reveal structures that the human eye cannot easily detect. When high contrast enhancement is applied and the average glow of the coma is subtracted, faint patterns inside the dust cloud become visible. Today's enhanced images revealed one of those patterns. Very close to the nucleus, the dust forms a faint spiral that coils outward in a slow curve. Under standard imaging, the spiral does not stand out. It looks like part of the normal, uneven distribution of dust. But once the brightness is processed carefully, the spiral shape becomes clear. It is a curve winding outward like a loose twist, not a random scatter of particles. Structures like this are important because they show that the dust leaving the nucleus is not moving outward in straight lines. Instead, it is following a turning path shaped by rotation. A spiral in the inner coma means two major things. First, it confirms that the nucleus is rotating in a consistent direction and at a speed strong enough to imprint its motion on the dust around it. The dust leaving the vents does not simply spread outward. It curves as the nucleus turns, creating a trace of its motion in the space around it. Second, the spiral suggests that the jets themselves are producing material in a repeating pattern. When the vents release material at regular intervals, the rotation pulls this material into a curved line. Over time, the curve extends outward as newly released dust pushes older dust farther away. This creates a layered spiral effect, with each loop representing material released during a different stage of the rotation. Seeing a spiral also supports the idea that more than one vent is active. When only a single vent dominates, the dust often forms a narrow, stable feature. But when multiple active regions release dust at different phases of the rotation, their contributions combine to create a twisting structure. The exact shape of the spiral depends on the rotation speed, the angle of the jets, and the rate at which dust leaves the surface. This is why today's discovery is important. It provides a visual confirmation of the mechanical processes hinted at by the timing changes in the brightness curve. Spiral patterns are not common, but they have been detected in a few small bodies when conditions are right. They require steady activity and a rotation speed that remains within a certain range. If the body rotates too quickly, the dust spreads too fast to form a clear pattern. If the activity is too weak or irregular, the spiral does not form at all. The presence of a spiral in 3I Atlas means the forces shaping its motion are organized enough to produce a repeating structure. This aligns with the updated measurements, showing a shorter rotation period and an increase in the complexity of the brightness curve. Taken together, the faster rotation, the growing second peak in the light curve, and the spiral in the inner coma all point toward the same conclusion. The object is experiencing a shift in the distribution and strength of its active regions. These changes do not happen randomly. They follow from physical processes tied to sunlight, internal pressure, and the irregular shape of the nucleus. As the jets adjust in strength and position, the forces applied to the nucleus create a twisting motion that appears both in the timing of the rotation and in the visible structure of the dust. Each new piece of data supports the next, forming a chain of evidence that the rotation state is evolving in a measurable way. What makes the current moment notable is that all three signs appeared together. The shortened rotation period alone would already point to a shift. The change in the brightness curve would suggest that the active regions have changed, and the spiral would indicate a rotating dust release. But when all three appear at the same time, the interpretation becomes stronger. They confirm that the forces acting on the nucleus are not only changing, but also shaping the dust around it in a pattern that we can detect. The spiral makes these internal and rotational changes visible, offering a rare chance to see how a small body from outside our solar system responds to solar heating during its passage. And that spiral is telling us two really important things at the same time. The spiral pattern close to the nucleus carries two major messages that allow researchers to understand what is happening inside the comet more clearly. The first message comes from the fact that the jets are steady and strong enough to form repeating structures in the dust as the nucleus turns. For a pattern like this to appear, the escaping material must be released with a direction and timing that stays relatively stable from one rotation to the next. Even small jets can alter motion, but only the stronger and more persistent ones leave marks that extend outward in organized curves. As the nucleus rotates, the dust pushed away by these jets follows a shifting path because the release point itself is moving. Over time, this movement creates a curved formation instead of a straight line. When the curve repeats across several rotations, it forms a spiral. Seeing such a pattern means the jets are behaving in a sustained and predictable way and are releasing enough material to shape the dust near the nucleus. The second message comes from the way the spiral has changed over time. Earlier images showed a looser spiral, with the dust spreading in gentler arcs. Now, the new processed images show that these arcs have tightened. The curves wind closer together, creating a more compact coil around the nucleus. This tightening is important because it reflects the rotation pace of the nucleus itself. When the nucleus spins more quickly, the dust expelled by the jets does not drift outward as slowly as before. Instead, the rotation pulls the released material into a sharper path, causing the curve to wrap more tightly. A tighter spiral is a clear sign that the spin rate is increasing. This happens because the dust is still moving away from the nucleus, but the nucleus is turning faster as the dust expands outward. The faster the rotation, the more tightly the pattern forms. For this reason, the spiral structure supports what the brightness curve already showed. The comet is spinning faster than before. These visual findings line up with three measurable facts. First, the rotation period is becoming shorter. The timing of the brightness peaks has shifted, and this shift appears consistently across multiple datasets. The rotation is not simply fluctuating, it is speeding up. Second, the increase in the secondary peak in the brightness curve indicates that a second active region on the nucleus is releasing material in a steady and significant way. The nucleus is no longer dominated by a single vent. Third, the spiral pattern forming in the dust around the nucleus has become more pronounced and more tightly wound, matching what would be expected if the nucleus was spinning more quickly. Each of these observations is valuable on its own, but all three together form a coherent picture. They show that the comet is undergoing a real and measurable change in its rotation state. When NASA summarized its update, the findings were included but not highlighted heavily. The information was there for anyone reading carefully, yet the tone of the update did not draw attention to the significance of the change. The key point is that the comet is not only changing its brightness or the shape of its coma, it is not just adjusting the amount of dust and gas that escapes from its surface. The object is altering how fast it rotates. This is a deeper level of change, affecting the entire structure from the surface to the interior. A change in rotation is not something that can be dismissed as a minor fluctuation. It reflects real adjustments in the forces acting on the nucleus. Understanding why this is important requires a closer look at what comet nuclei are. These bodies formed in the early history of the solar system and the regions beyond it. They contain rock fragments, grains of dust, frozen gases, and complex molecules locked together in loose arrangements. Their surfaces can appear solid, but the interior structure is usually fragile. The material inside is held together mainly by ice that forms bonds between grains and by the comet's own weak gravity. These bonds have very low strength, especially when compared to rocky planets or dense asteroids. The internal spaces can be filled with voids, cracks, and pockets of gas. That makes the nucleus more like a porous mixture of particles, rather than a solid monolithic object. Because the structure is weak, a comet nucleus has limits to how fast it can spin before the outward force generated by rotation becomes greater than the strength holding it together. This outward force increases as the rotation rate increases. If the rotation becomes fast enough, areas of the surface can start to shift. Loose material may move toward the equator, where the outward force is strongest. Slopes may become unstable. Ridges can collapse. Over time, the stress from fast rotation can move from the outer layers into deeper parts of the nucleus. If the stresses exceed the internal strength at any point, cracking begins. Once cracks form, they can grow quickly because the internal structure is already weak. Gas trapped inside the nucleus can escape through these cracks, expanding them even further. In some cases, this process leads only to surface reshaping. But in more extreme cases, the nucleus can split into two or more pieces. When the breakup begins, the material does not simply drift apart. The pieces can accelerate away from each other because of the forces stored in the rotating body. Observations of other comets in our solar system have shown this sequence clearly. The same pattern repeats. The rotation rate increases over time. The nucleus shows signs of shifting or developing new active regions, and then the breakup begins. The fragmentation often happens suddenly because the last stages involve a rapid loss of internal strength. Once the internal pressure or the outward pull becomes too strong, the body cannot resist the forces any longer. The fact that 3I Atlas is showing signs of increasing rotation matters because it places the nucleus closer to this type of mechanical instability. The presence of two strong active regions means multiple jets are exerting force on the nucleus from different directions. These forces do not cancel each other out evenly. Instead, they add complexity to the rotation. The brightness curve shows the timing shift, while the spiral structure shows the dust responding to that shift. In combination, the data points toward a steady and increasing spin-up. Small objects like comet nuclei do not have the same resilience as larger bodies. When a planet rotates, its gravity keeps its structure intact. When a small, icy body rotates, gravity is too weak to offer strong support. The only thing resisting the outward pull is the strength of the bonds between particles. If the spin continues to increase, those bonds can fail. Even a slight increase in rotation rate can push a weak nucleus closer to its breaking point. To understand this more clearly, imagine the forces acting inside such an object without relying on imagery. When the nucleus rotates, every particle inside it feels an outward pull. Particles near the surface feel this pull most strongly because they are farthest from the center. If the rotation accelerates, the outward pull increases. At the same time, solar heating can weaken the bonds between particles by warming the ice that holds them together. This means the nucleus can become weaker as the rotation becomes stronger, which is a combination that often leads to instability. Breakup events in comets follow a pattern that researchers have studied for decades. First, there is a slow increase in rotation rate. This change can be detected only through detailed measurements. Next, vents on the surface become more active as sunlight reaches fresh layers of ice. Then, the internal pressure builds, and surface structures such as ridges or mounds may begin to change. At this stage, the nucleus still appears stable, but once the threshold is crossed and the outward force exceeds the strength of the material, the breakup happens. Sometimes the body splits along a structural weakness, and sometimes it breaks into irregular pieces. In all cases, the process follows the same general path: slow spin-up, apparent stability, and then a sudden fracture. This is why the recent updates deserve attention. The comet is not only brightening or shifting the orientation of its tail, it is undergoing physical changes that tell us about the forces inside it. The spiral pattern around the nucleus is a visual sign of these changes. The brightness curve is a numerical sign. The activation of a second region is a geological sign. Together, they form a set of observations that match the early stages of known breakup sequences, even though no one can yet say whether this comet will reach that point. The important point is that these processes are not hypothetical. They are measurable, repeatable, and consistent with how small icy bodies respond when their internal balance shifts. The rotation increase may continue slowly, or it may stabilize if the jets weaken. But an accelerating spin suggests a growing imbalance, and such an imbalance has consequences for bodies with weak internal structures. This leads to the final idea in this sequence. When a comet shows signs of increasing rotation, expanding activity in multiple regions, and the formation of tight spiral dust patterns, these are not separate curiosities. They are linked signs of mechanical stress. That connection is why researchers are taking these updates seriously. And that connection is the part that should really make us all sit up and take notice. The changes happening inside this comet would be notable under ordinary conditions, but they are even more significant when placed in the context of everything the object has already been through. It has survived conditions that push many comet-like bodies to the edge of structural failure. When it moved through perihelion, which is its closest approach to the Sun, the nucleus entered a region of intense heat and solar radiation. During this phase, sunlight becomes strong enough to reach deep into the surface layers, warming the ice and forcing gas to escape. These forces can lift large amounts of dust and reshape the glow around the nucleus. The object endured this period and continued along its path, releasing massive jets of material as it did. The scale of those jets was larger than expected, and the rate of release surprised many researchers following the data. Some jets expanded the coma so quickly that its appearance changed over short intervals, making the outer region around the nucleus look different from one observation to the next. As the coma changed shape, the direction of the forces acting on the comet shifted. Jets that were strong enough to push material into space were also strong enough to alter the slight thrust that affects the motion of the comet itself. When a jet becomes active, it exerts a small push on the nucleus, and the direction of this push depends on the position of the vent. If multiple vents switch on and off at different times, the overall thrust direction can shift. Observers saw this happen repeatedly. The activity patterns changed in ways that made the comet appear to flicker between different modes. Sometimes, the jets were strong and steady. Other times, activity dropped off quickly, leaving a quieter coma. These switches happened often enough that researchers treated the object as one of the more variable interstellar bodies ever observed passing through the inner solar system. Now, after surviving these cycles of heating, venting, shifting thrust, and fluctuating activity, the comet is showing a steady increase in rotation rate. This new change comes after a long sequence of earlier events that would already place considerable stress on a small body with a fragile internal structure. The fact that the rotation is now increasing slowly and consistently suggests that the forces acting on the nucleus have not settled into a stable pattern. Instead, they appear to be driving the comet toward a new rotational state that may or may not be sustainable over time. There are only a few broad ways this situation can develop from here. In the best scenario, the active regions on the nucleus could transition into a more balanced pattern. If two dominant vents continue to operate with similar strength, and with jets that act at points along the rotation where they counterbalance each other, the nucleus might reach a new rotational equilibrium. In such a state, the push from one vent could partly cancel out the push from the other. If this happened, the rotation rate might stop increasing. The comet would remain intact and exit the solar system as a slightly faster rotating version of itself. The structure would remain stable, and the nucleus would continue its interstellar journey long after it leaves the Sun's gravitational influence. But the activity patterns so far do not show signs of stable balance. Instead, they show signs of shifting behavior and new structural developments. If new vents open in different locations, they could introduce new thrust angles. Each new vent would apply force in a direction that might differ from the earlier ones. This could cause the rotation rate to continue increasing, especially if the new thrust does not counterbalance the existing forces. If the rotation increases, the spiral structure in the dust could tighten even more. This would be consistent with a faster spin and would also indicate that the dust is responding to stronger rotational influences. If the spiral continues to develop in this direction, and if the jets remain active at varying intensities, the nucleus could enter a state of significant mechanical stress. It is important to understand how these stresses interact with the comet's internal structure. Comet nuclei are ancient objects. They formed in the early stages of the solar system or in similar environments elsewhere in the galaxy. Their surfaces have been exposed to cosmic rays for extremely long periods. Cosmic rays can alter the chemistry of the outermost layers, making them harder and more compact than the material inside. This outer layer may seem strong, but it covers an interior that is often porous and fragile. The inside of a comet nucleus can contain cracks formed by thermal stress. As the comet approached the Sun, the temperature difference between the cold of interstellar space and the heat of the inner solar system caused expansion and contraction in the materials. These repeated changes can widen older cracks or create new ones. Ices inside the nucleus can warm unevenly, and gas trapped inside can build pockets of pressure. These factors all contribute to a structure that may appear solid, but is mechanically weak on the inside. When such an object experiences increasing rotational force, the weak regions are placed under strain. Every increase in rotation increases the outward pull that each particle inside the nucleus experiences. The outer layers feel this force the most because they are farthest from the center. As the rotation speeds up, loose material can begin to shift toward the equator. If the internal cracks are already large, or if the material between particles is not strong enough, these shifts can accelerate internal weakening. Over time, the stress can affect deeper regions of the nucleus. As gas vents continue to operate, they remove mass from the nucleus and change the distribution of weight. These changes cause further adjustments in how stress is spread across the nucleus. At some point, the combination of internal cracks, thermal expansion, uneven heating, and increasing rotation may reach a threshold. When this threshold is crossed, areas inside the nucleus may no longer be able to resist the outward pull. Surface layers can slide. Features near the equator can slump inward or collapse. If the stress overcomes the strength of the material, the nucleus can split. The breakup process often begins quietly. The rotation continues to increase. New vents open. Older vents expand. Surface patterns change. Then, suddenly, the nucleus breaks along its weakest line. This sequence has been observed in several comets within our solar system. The details vary, but the overall pattern is well documented. First comes the slow increase in rotation rate. This can go unnoticed at first because the changes are small. Then comes the development of new active regions. sometimes in places where sunlight begins to warm deeper layers of ice. After this, the surface can shift or deform as the internal pressure and outward rotational force interact. Finally, the nucleus reaches a critical point and fractures. The fragments drift apart, sometimes slowly and sometimes quickly, depending on the forces involved. Because this process is known, researchers approach rotation changes with caution. NASA has not used the term breakup in its official statements. Instead, the language remains careful and precise. Phrases such as measurable evolution in rotation state and new evidence of changing internal torque reflect that caution. These phrases describe the data without predicting outcomes. They show that the rotation is shifting in a measurable way and that internal forces are changing. They do not say that the nucleus is heading toward breakup, but they make it clear that the internal mechanical behavior of the nucleus is evolving. When reading these statements, it becomes clear that the most important part of the update is not the brightness pattern, not the coma structure, and not even the presence of the spiral. It is the fact that the rotation is changing in a consistent direction. Among all the parameters that describe a small icy body, rotation is one of the most critical. A change in rotation can reshape the nucleus, alter jet activity, modify surface patterns, and increase internal stress. Rotation is also the factor that determines whether the structure can remain intact. If the rotation increases too much, the internal strength may no longer be able to support the outward pull. These new developments matter because they show that the rotation is not stabilizing. Instead, it is continuing to rise. The strengthening of the secondary active region adds to the complexity of the forces acting on the nucleus. The tightening of the spiral confirms that the dust is responding to a faster rotation. The earlier stresses the nucleus experienced during perihelion and through repeated cycles of activity may already have weakened the internal structure. Now, as the jets continue to release material and the rotation continues to accelerate, the mechanical pressure keeps building. The comet is an ancient object, shaped by long exposure to space. Its surface may have hardened over time, but the interior remains vulnerable to stress. As it rotates faster, the cracks inside may widen. Gas trapped inside may escape suddenly. Surface layers may shift. These developments interact in ways that can push the nucleus toward instability. The rotation change is not just another detail. It is a direct signal of the forces working inside the comet. The risk increases as the rotation speeds up. NASA's statements may avoid strong language, but the meaning is clear. The comet has changed again, and this time, the change involves rotation. Rotation is the one factor that can drive the nucleus beyond its structural limits. If the rotation increases enough, the forces acting on the nucleus can exceed its ability to hold together. Once that happens, the material will move in the direction of least resistance. Jets will no longer be the main source of motion. Instead, the internal structure will determine where the first fracture occurs. This is why researchers read these updates so carefully. They understand that increasing rotation is one of the most important indicators of mechanical stress. It is not a sign of danger in the sense of threat, but it is a sign of internal change that can lead to large-scale restructuring of the nucleus. The rotation is not just a number, it is a condition that affects every part of the comet. If it continues to rise, and if the internal strength cannot match the outward force, the nucleus can reach a point where the structure can no longer maintain its shape. This comet has survived extreme heating, rapid venting, shifting thrust, changes in activity, and cycles of stress. Now, it is facing a new challenge driven by rotation itself. And that is the one factor that can break a comet apart if it grows too strong, if it passes the point where the structural integrity cannot keep up with the mechanical forces. Over the next several days, and possibly for the next few weeks, the entire network of observatories will concentrate on monitoring every detail of this comet's behavior. The teams following it understand how quickly conditions can change and how important it is to collect continuous measurements when an object begins showing signs of rotational evolution. Any telescope with a clear view will contribute data. This includes ground-based observatories that track brightness changes through the night, instruments in orbit that can capture high-contrast views above the atmosphere, and specialized research facilities that have been dedicated to monitoring variations in small body rotation for decades. The goal now is to refine measurements with the highest possible precision, because the window for understanding these changes is limited. The comet is moving quickly along its path, and the physical processes inside it are shifting on timescales that require near constant attention. One of the most important tools for this type of monitoring is the light curve. A light curve is a record of how the brightness changes over time, and for rotating objects, it provides information about the rotation period. When the nucleus turns, the amount of light it reflects shifts as different regions face Earth. By collecting brightness measurements again and again, researchers build a repeating pattern that shows how long each full rotation takes. Right now, every fraction of a second matters, because the rotation changes are small but steady. Even a shift of a few hundredths of a second per cycle can signal that a new force is acting on the nucleus. These shifts may not seem large individually, but over many rotations, they accumulate into a measurable trend. To improve the accuracy of these light curves, observers will take long exposure images and combine them into stacked frames. Stacking images reduces noise, increases the clarity of faint details, and brings out patterns that would otherwise disappear into the surrounding glow. This is especially important for examining the inner coma, which holds the dust structures closest to the nucleus. The spiral pattern identified in the earlier images must be observed repeatedly to determine whether it becomes sharper, more organized, or more chaotic as the days pass. If the spiral tightens, that will support the idea that the rotation is continuing to speed up. If the spiral begins to distort or break apart, that could indicate instability in the jets or changes in the distribution of material across the surface. Another major focus will be orbit refinement. A comet's path through space is shaped mainly by gravity, but small bodies with active jets do not travel on purely gravitational trajectories. When a jet releases material in one direction, it exerts a force on the nucleus in the opposite direction. These forces are small, but when they occur continuously over long distances, they can alter the comet's trajectory in measurable ways. If the rotation rate increases and the jets shift direction or intensity as a result, the overall path of the comet can change. This is why orbit calculations must be updated regularly during periods of high activity. Small variations in thrust can compound over time, creating a motion that differs from the path predicted weeks or even days earlier. Many people do not realize how sensitive a comet's motion is to these forces. The popular image of a comet is a simple, ice-rich object that follows a long, predictable orbit around the Sunday. But in reality, active comets are more dynamic. Jets act like tiny thrusters. When the nucleus rotates, these jets turn with it, causing the direction of the thrust to shift continuously. This makes the overall force pattern complex. If the rotation rate increases, the motion becomes even more difficult to model. Observers must therefore track the rotation period and the jet activity at the same time. Only then can they accurately forecast how the comet will move. If the rotation period continues to shorten, if the spiral continues to tighten, and if the brightness peaks drift farther apart due to the growing dominance of two strong active regions, then researchers will know that the changes seen today are not a temporary irregularity. They will represent an actual transition into a new phase of activity. Data rarely aligns by coincidence across multiple independent indicators. When brightness, dust structure, and rotation pattern all shift together in a consistent direction, the explanation usually involves a real physical process acting on the nucleus. These processes do not correct themselves quickly, and they often signal deeper changes in the internal structure. This next phase would mark a point where the comet is not only changing how it appears from Earth, but is also changing in a mechanical sense. When astronomers talk about mechanical changes inside a comet, they refer to the distribution of pressure, the strength of the material, and the forces that act on the structure. If the rotation increases, the internal stresses rise with it. The material inside the nucleus may shift slightly, cracks may widen, and the orientation of active vents may change. When these internal adjustments occur at the same time as visible changes in the coma, it becomes clear that the evolution is not limited to the surface. This is part of what makes the current observations so scientifically valuable and also challenging. We rarely witness a comet undergoing such rapid evolution while still being actively monitored. Most comets follow predictable patterns that allow researchers to model their behavior with confidence. But 3I Atlas is different. It entered the solar system from beyond our sun's gravitational domain, possibly formed under conditions that do not match the icy bodies in our own system. Its material composition, internal structure, and thermal history may all differ in ways that influence how it responds to heating and to the forces created by its own jets. Observing these changes in real time allows researchers to test models that have rarely been applied to interstellar objects. Each new measurement helps refine our understanding of how small bodies evolve when influenced by jets, heat, and spin simultaneously. Some of the processes now occurring in 3I Atlas may resemble those seen in solar system comets, but others may challenge long-standing assumptions. That is why this period is important. It provides a natural experiment that cannot be repeated on demand. The central scientific question now is whether the comet will stabilize or continue down a path that leads to increasing stress. If the jets find a balance, exerting forces that bring the rotation into a new steady state, then the nucleus may remain intact. The object would continue its outward journey, eventually leaving the solar system and returning to interstellar space. In this case, the spin-up would be only a phase, a temporary period of adjustment, before the comet resumes a more predictable behavior pattern. However, the other possibility is that stability will not be reached. If the active regions continue to grow, if new vents appear, or if the thrust direction shifts again, the rotation rate may continue to rise. Each new change introduces more complexity into the mechanical system. A faster rotation means stronger outward pull on the nucleus. Increased stress raises the likelihood of internal failure. The spiral structure tightening over time would be a clear sign that the rotation is approaching a level where the nucleus may no longer be able to support itself. These possibilities are not hypothetical concerns. They are grounded in observations of other comets that have shown similar early signs before undergoing structural failure. When the rotation increases steadily and the internal stress rises, a comet can fracture along one of its weaker zones. The fracture may begin as a small separation, sometimes too subtle to detect immediately. But once it begins, the forces that caused it tend to amplify the separation, leading to a breakup. Because 3I Atlas has already experienced extreme heating, rapid venting, and structural stress during perihelion, the risks of instability are amplified. Every night, researchers will analyze the latest measurements to see how these indicators evolve. They will check the brightness curves for increasing asymmetry. They will check the spiral structure for signs of tightening or distortion. They will refine the orbital predictions with every new data point. They will run simulations to examine how different combinations of jet activity could influence the rotation. This sustained attention reflects both the scientific value of the object and the uncertainty that surrounds its future. Watching these changes unfold in a body that originated outside our solar system adds another layer of significance. Interstellar objects provide rare insights into environments and processes that cannot be observed directly from Earth. They carry information about their formation and about the regions they passed through before arriving here. The evolving rotation of 3I Atlas may reveal how objects formed around distant stars respond to forces that differ from those in our own system. This is why scientists continue reviewing new data with such focus. They understand that the results may inform not only the study of comet-like bodies, but also the study of interstellar materials. The uncertainty surrounding this comet's future is part of what makes the situation compelling. The question is no longer only about how bright it is or how the coma looks. The question now involves the behavior of the nucleus at a structural level. Will it stabilize? Will it continue to increase its rotation rate? Will the internal stresses reach a point where the nucleus fractures? None of these outcomes can be predicted with complete confidence at this stage. The forces acting inside the nucleus depend on conditions that cannot be measured directly, and the material properties of interstellar objects are not yet fully understood. Researchers frequently revisit their models as new data arrives because comet behavior can shift quickly. The complex relationship between venting, heating, and rotation means that even small changes can have significant consequences. This is why the analysis now extends beyond conventional comet models. Scientists are preparing for outcomes that do not fit the usual expectations, because the object itself may differ in key ways from typical solar system comets. The tools they use are based on decades of research, but they may need to adapt these tools as more information arises. Despite the challenges, the scientific opportunity is immense. Observing these changes allows astronomers to see physical processes unfold that are normally hidden or too slow to observe within a human lifetime. 3i Atlas offers a chance to study how interstellar materials behave under the influence of solar heating, jet activity, and rotational stress. Regardless of the final outcome, the observations collected during this period will deepen our understanding of how small bodies respond to complex and shifting forces. One final point is clear from all the data gathered so far. The comet has not reached a state of stability. It is not slowing down or settling into a predictable pattern. Instead, it is continuing to evolve. Each new measurement reinforces the idea that the processes affecting the nucleus remain active. The story of this comet is not nearing its conclusion. It is unfolding in real time, with new layers of information emerging each day. And at this moment, nobody knows exactly how it's going to.